Afternoon to everybody. So I'm Raju. I'm talking about impact of data assimilation on the prediction of monsoon rainfall. So Indian summer monsoon is most energetic phenomenon in the tropical climate system. It has lot of impact on the different aspects like power generation, water resources management, and agriculture, and ultimately the economy of the country. So this Indian summer monsoon exhibits wide spectrum of variability from daily to decadal and even centennial timescales. This Indian summer monsoon, it is not a steady state. It fluctuates within the season between the periods of enhanced rainfall over the central Indian region and North Bay of Bengal. It is referred as active spell, and also suppressed rainfall period as referred as break spell. So this is what we call as monsoon intra-seasonal oscillations. So these intra-seasonal oscillations of the Indian summer monsoon plays a major role in influencing the seasonal mean monsoon characteristics and its intra-annual variability. So this prediction of active and break spells of the Indian summer monsoon 2 to 3 weeks in advance is great importance for the food production and water management of the country. But it is currently it is not yet solved. So far, many models have performed poorly in the simulation of monsoon intra-seasonal oscillations. So in this regard, researchers are making constant efforts to predict the Indian summer monsoon rainfall by using dynamical models and empirical models. But recent studies some recent studies suggested, and some recent studies showed that if you assimilate the satellite, if you improve the initial conditions, the prediction of rainfall will improve. With this background, we have tried an experiment with dynamical model. So this is the model details. Model type is primitive equation model, and I'm used weather research forecasting model with ARW core. So this is domain which covers the large scale monsoon, and this is the different physics options which I used in this study. And my initial and boundary conditions is taken from NSEP, NCAR, final analysis, which has the resolution 1 degree by 1 degree. So this data assimilation I used in this study. The technique is 4-dimensional data assimilation. It is a continuous data assimilation technique which is to run a full physics model while incorporating observations. Thus, the model equations assure a dynamical consistency while the observations keep the model close to the true conditions and make up for errors and gaps in the initial analysis and deficiencies in the model physics, which means that model state is relaxed towards the observation state by augmenting some of the prognostic equations with forcing terms based on the difference between the observed state and model state. This is the equation. This is the predictive variable. This is the tendency term due to the physics. This is an nudging term, weighting coefficient with respect to space and time. So this technique I used, and I have done like this experiment for 10 days, 1st to 10th July for the monsoon 2010. So this is the period which is transition from the break to active condition. Generally, models can predict the break better than active spell. So I have seen during the active period. These are the different observations used in my study. I have taken upper air observations and surface observations from different data sources during the period. This is the flow of the data assimilation. This is the assimilation window from 26th June 2010 to 1st July 2010. These are the different data sources. So first I assimilated at the 26th June at 00 UTC and give the pre-forecast. This is pre-forecast period and pre-forecast period. So I assimilated again, I injected available observations particular that day, and this will be continue up to here, and then pre-forecast will start from July 1st to 10th July. So this is the some results. Vorticity, this is a low level vorticity, which is a very important dynamical component. If you see, this is a model, this is control run. This is with FDD assimilation, and this is observations in independent product era. So if you see that during the period, instability is very high over this central Indian region. So which is, the model, it is produced a very irregular pattern, but after assimilation it produced in a smooth pattern over this region.
Sorry, what does ERA stand for?
Sir?
What does ERA?
Okay, ECMRWF reanalysis product observations.
That's what we use as data.
Yeah. This is the spatial distribution of precipitation. This is averaged from 1st July to 10th July. This is again control with assimilation.
Can you go back to one second?
Yeah. No, just.
Use the page of data on the top.
Yeah.
The left top is your compared without assimilation.
Yes. Without assimilation, with assimilation, compared with observations.
This is your baseline. This is what you're comparing with.
Yeah, this is comparing with respect. These two are comparing with respect to this. This is observations. And this is the model.
It's not observation.
No, it is but we are considering as observations. This is considering as observations. Yeah. This is the spatial distribution of precipitation averaged from 1st to 10th July. This is again control with assimilation with respect to IMD and TRMM. So after assimilation, see, this region, the control run shows very high overestimation in this region and with respect to observations. But after assimilation, this has improved here, and also if this region observation shows very less rainfall, but this model shows a bit high rainfall. But after assimilation, it also improved, and the spread is in the control run. The spread is limited up to here. But after assimilation, this spread is extended towards the north. This is just daily time series over the central Indian region from 69 degrees east to 88 degrees east and 18 degrees north to 28 degrees north, which we consider as central Indian box where the variability is very high. So this control run, and this red one is IMD, and this is TRMM, and this is FDDA. If you see these two this FDDA and control run, this control run showing very high magnitude whole the period, and after the assimilation, this is suppressed, and it is reasonable comparison with the other observations like TRMM and IMD. And these are, yeah. What? Control run without assimilation. No, it is not innovation. Just we have, this is the, model range 45 kilometers. I have shown that details. No, this is different. It is really.
So how you compare the four different emission quantities each other?
But people.
Are you use some interpolation or just comparing?
This is area average over this box, over central Indian box. Is it okay? This is some statistics. Mean with respect to IMD without assimilation and with assimilation. So without assimilation, the mean is showing that around 12.865. So after assimilation, this mean is reduced 9.123, which is close to the observations. If you see the standard deviation and RMSE, if you see the without assimilation, it is showing that 5.96. After assimilation, it is came 3.62. And many dynamic, yeah. Yeah, okay. This is all. It's all fine. Many dynamical models will not, it will not produce vertical structures. It is lot of disparity. So if you see this is the vorticity component same over the same central Indian domain. vorticity and temperature and water vapor mixing ratio. This is control run. This one control run. This is again error, and this is with assimilation. So if this region all over this after assimilation, this line is come close to the observations, and with respect to temperature and water vapor mixing ratio also. I think so. Thank you.
Does IITM build its own model also? Do you have your own model running? Do you have your own model running of the Indian Ocean and the atmosphere? I mean, that's what I don't. Sorry, you mentioned so many models that I'm a little mixed. Sorry. Okay. WR, which is the NCAR model, right? So that's what you're using is the NCAR model. So you're adapting it to so you're using the global NCAR model, and then you're assimilating in the WRF model. Okay, and you're assimilating only rainfall?
No, sir, only UV, winds and temperature.
Wind and temperature.
UVW, T and Q.
Okay.
Model with assimilation of these 4 quantities and comparing it with the ERA as truth. ECMWF reanalysis as truth is not being assimilated. Only observations from IMD and so on are being assimilated. And so ECMWF reanalysis is independent, so to say. Comparison